Welcome to this explainer. We're jumping right into what I like to call Earth's high-tech planetary engine. We feel the output of this engine every single day. We just call it weather, but the mechanics operating behind the scenes, or, above the clouds and across the oceans, are just absolutely fascinating. Let's look at the digital blueprint of how solar energy and our atmosphere drive this whole system.
Okay, here's our roadmap for today. We're starting with fueling the engine, then the atmospheric shield, the Coriolis steering wheel, global wind belts, land masses, and local weather, and finally, the threat of storm surges.
Section 1. Fueling the engine. To really get how this global weather machine works, we've got to start by looking at its primary power source.
So, Earth is a sphere, right? Which means sunlight doesn't hit everywhere equally. This creates what we call a solar footprint. Down at the equator, sunlight strikes directly at a super high angle. It's literally concentrating a massive amount of solar energy into a tight, focused area, heating it up incredibly fast. But think about the poles. The exact same amount of solar radiation hits up there, but at a very low, glancing angle. That forces the energy to spread out thinly across a way larger surface area. Plus, it has to travel through way more atmosphere just to get there, losing punch along the way.
And building on that heat disparity, we've got the albedo effect. Think of this as nature's giant mirror. Because those high latitudes are covered in bright white stuff, snow and ice, a huge chunk of that already weakened solar fuel gets bounced straight back into space. So the engine runs incredibly hot at the equator and freezing cold at the poles. That massive temperature difference, that's the fundamental imbalance that powers literally everything else we're about to talk about.
Section 2. The atmospheric shield. Let's see how all this intense solar heat is captured by the engine block surrounding our planet.
Now, you might assume the air we breathe is mostly oxygen, but surprisingly, it's not. It's actually nitrogen, coming in at just over 78%, followed by oxygen at roughly 21%. The rest of it, argon, carbon dioxide, and other trace gases, they make up just about 1% combined. But wow, do not let those tiny numbers fool you. Even trace gases, especially carbon dioxide, play a huge outsized role in trapping the Earth's heat.
The really crucial point here is the massive contrast between the bottom two layers of this atmospheric shield. The troposphere is essentially the ground floor, reaching up about 12 kilometers. Now, because it's heated by the Earth's surface radiating warmth from below, it actually gets colder the higher up you go, dropping to a freezing minus 60 degrees Celsius. This rapid cooling creates incredibly turbulent, mixing air, and that turbulence is exactly why all our weather happens right here. But right above it is the stratosphere. And the rules completely flip. Because it contains the UV-absorbing ozone layer, this section actually heats up with altitude. It acts almost like a giant lid sealing in the chaotic weather below.
Moving on to Section 3, the Coriolis steering wheel. We've got our fuel, we've got our engine block, now it's time to set this massive machine spinning.
Okay, the Coriolis effect can definitely be a tricky concept, but we can break the physics down into 3 simple steps. Imagine you're standing right on the equator. You are currently spinning eastward at a staggering 1,674 kilometers per hour. But if you travel north or south towards the poles, the Earth's rotational speed drops off. So if a mass of air starts moving from the super-fast equator toward the slower poles, it carries that high-speed eastward momentum right along with it.
Because this air is flying over land that's actually spinning slower than the air itself, it appears to curve. Moving air veers dramatically to the right in the northern hemisphere and to the left in the southern hemisphere. Now, technically, it's an optical illusion caused by our rotating perspective, but I promise you, its impact on our global weather engine is absolutely real.
Section 4. Global wind belts. Let's look at how this steering mechanism creates global air circulation.
If the Earth didn't spin at all, warm air would just rise at the equator, travel to the poles, sink, and return. Just one giant simple loop. But because of that Coriolis deflection we just went over, that massive hemisphere-wide airflow gets completely broken up. It fractures into 3 distinct, smaller convection cells per hemisphere. It's kind of like upgrading a basic single-cylinder engine into a much more complex, high-performance multi-cylinder machine. And these intersecting cells give us our major wind and pressure belts. Where air is actively rising, so at the equator and at 60 degrees latitude, we get low pressure. Low pressure means heavy clouds and lots of rain. On the flip side, where cool air sinks at 30 and 90 degrees, we get high pressure, which brings clear, dry, beautiful skies. The air rushing along the surface between these pressure zones give us our really reliable winds, the trade winds, the westerlies, and the polar easterlies. Oh, and right on the borders where the air is mostly just moving straight up or straight down, like at the equator and 30 degrees, we get the doldrums and the horse latitudes. Early sailors absolutely dreaded these spots because of their notoriously weak, dead winds.
Section 5, Land Masses and Local Weather. Let's zoom in a bit. What happens when this planetary wind engine crashes into giant continents?
Well, continents act like massive roadblocks, and their varying temperatures completely hijack local winds. Take the Asian monsoons, for example. We're talking about entire climate systems dictated by seasonal wind shifts across these vast land masses. In the summer, the land gets scorching hot, the air rises, and moist ocean winds are drawn in from the southwest, dumping heavy rains. But in the winter, the whole pattern just flips. The land cools down, creating high pressure, and dry winds blow out from the northeast.
And you can actually feel a miniature version of this monsoon effect if you just take a trip to the beach. On a local scale, it comes down to a simple fact. Dirt heats up a lot faster than water. During the day, the land gets hot, the air above it rises, and that draws in those refreshing, cool sea breezes we love on the coast. At night, the land cools off faster than the ocean, and the breeze flows right back out to sea. It's the exact same thermal engine, just scaled down to a daily, local level.
Topography plays a massive role here, too. When moist ocean winds hit elevated land, like, say, a mountain range on an island, the air has nowhere to go but up. As it gets forced upward, it cools down, the moisture condenses, and it just dumps huge amounts of water. We call this orographic rain. The windward side of the mountain gets totally soaked, while the air flowing down the other side, the leeward side, is bone dry because it's been depleted of literally all its moisture.
Section 6, the threat of storm surges. For our final section, let's examine what happens when this planetary engine gets pushed to its absolute limits. When extreme low-pressure systems feed off the intense heat of warm ocean waters, they can grow into violent hurricanes, and these churning winds physically push massive walls of ocean water right ahead of them. When this wall collides with a coastline, especially if it happens during a high tide, it generates devastating storm surges. Guys, this isn't just a big wave breaking on the beach. This is the ocean level itself rising up and aggressively flooding inland.
It really is a terrifying convergence of forces. The interaction of gravity, the physical shape of the coastlines, and, you guessed it, our old friend the Coriolis effect all work together to trap and rotate massive amounts of water. The Coriolis effect actually forces water against the coastlines, piling it up and radically amplifying the flooding. It's the sheer, raw, mechanical force of the atmosphere imposing its will directly onto the ocean.
So we've seen how solar fuel, atmosphere chemistry, planetary rotation, and massive land masses all interlock perfectly to create our global climate. Which leaves us with a pretty crucial, thought-provoking question to end on. We know that even tiny trace gases in our atmosphere manage the Earth's entire heat budget. So if we keep altering the chemical makeup of our atmospheric engine block, trapping more and more of that heat, how exactly will this high-tech planetary engine rewrite the rules of our global weather? Definitely something to think about. Thanks for joining me on this explainer, and keep questioning the world around you.